I will talk a little bit about the quantum well and superlative solar cells. And there is nothing like to start with two wonderful pictures from my university, where the first thing to highlight is the sun rising. That is wonderful. And the second is that university is betting on the renewable energy. That is a wonderful thing. In this talk, I will first present the energy concern. After that, the kind of generation, the types of solar cells generations, the quantum well solar cells, and the superlative solar cells. Results will be presented on the aluminium, gallium arsenide, as well as gallium indium nitrogen arsenide. And finally, the proposal of quantum well and superlatives in the case of crystallized solar cells. As you very well know, energy is one of the big problems of this century. If we are here, it's thanks to energy. In fact, without energy, we will not be here. All of us have used some means of transportation to come here. Besides, without energy, there will be no electricity to present this talk, for example. And we all know that fossil fuels are run over. Therefore, it is required to find a new source of energy that will be less dangerous to the earth crust. In this case, renewable energy are welcome. In particular, solar cells are attracting the attention from the scientific community from recent years, and in this case we will talk about the solar cells. When it comes to development, energy is an important point. We can see that a developing country needs energy. Without energy, there is no development. Therefore, we will talk about solar cells. Solar cells is a relatively cheaper way to obtain energy from the energy of the sun. The main idea is to obtain the energy of the sun and its direct transformation to electricity. And unlike other means to obtain energy, this is a direct transformation. In this chart, it is displayed the summary of the different kind of solar cells and their behavior with time. We can see the emerging solar cells such as quantum dots, crystallized, organic solar cells, dye-sensitized solar cells, which are reaching efficiency value about 12%. There are other kind of solar cells like gallium arsenide, 4-junction solar cells, 3-junction solar cells that are not so that have many years in study. Of course, in comparison with silicon, they are not too old. And in the case of silicon, which is a known established technology, we can see that efficiency is about 25%. And what is more important from this chart is the fact that 4-junction solar cells are the ones that are reaching the highest solar cell efficiency, which is about 44% of energy conversion. This kind of solar cell is mainly based on 4 junctions, which have different band gaps so that each solar cell can absorb part of the solar spectrum and to increase the solar cell efficiency. And we will see later, there is some problems. One of the problems is the thermalization. So if we use a 4-junction solar cell, the thermalization problem is reduced, as well as the losses of energy of photon with energy lower than the band gap. In In a very broad way, solar cells can be summarized in 3 generations. Not all photovoltaic community agree with these 3 generations, but it is displayed in that way to simplify the explanation. The first generation is mainly based on silicon monocrystalline and polycrystalline. As well as a plus to this technology, it is a well-known technology. That is, silicon is the father of the microelectronics. Therefore, the wafers that do not fulfill the high purity is a waste for the microelectronics and is used in solar cells. In this case, it is very difficult to fight against silicon solar cells. But one of the points of the silicon solar cell is that this technology is very, very expensive, which is mainly based on Czochralski method. One important point is that efficiency of silicon have reached value of 25%, and in addition, silicon is the second element more abundant in the air crust. Therefore, it is quite difficult to replace this technology. But silicon is not the adequate material for solar cell applications, because silicon presents in indirect bandgap transitions. Therefore, that makes that absorption coefficient be very low, and therefore higher width or sum of absorbed material is required. In this case, about 500 micrometers. We will see that in the case of the second generation solar cell, about 4 micrometers is enough to make a solar cell, because this is a result of the direct bandgap transitions. Like the silicon, this is considered in the second generation of solar cells to improve the efficiency. Considering the problem of the first generation solar cells, the scientific community focus their attention in materials such as cadmium telluride, 6-castoreite, and more recently the perovskite ones. This technology have more adequate physical property for solar cells applications. Besides, the processing cost of this kind of solar cell is relatively lower than the silicon one. In this sense, it is more, this kind of technology is better to be used, and the processing cost will be reduced in the case of these panels. However, in some cases, efficiencies are not as high as in the case of silicon. And we see that efficiency are about 22% for cadmium telluride and 6%. But in the case of castoreite, it is in 12.6%, very low. But research is ongoing to overcome this limit. But what is more important is the theoretical limit for this kind of generation, for both generations, the first one and the second one, is 28%. It's a relatively low efficiency, which is obtained according to the Shockley-Queisner limit. In this sense, it is important to study the main loss mechanisms in this kind of solar cells. The first one is that photons with energy lower than the bandgap are lost. This is why this is a result of the semiconductor is not able to absorb energy that are lower than the bandgaps. This is a quantum rule. On the other hand, there are thermalization losses. That is, our solar cell only needs a photon that with energy equal to the band gap. If energy is higher, this energy is lost by means of thermalization. In this case, thermalization accounts to a 30%, while photons with energy lower band gap accounts to a 20%. There are other losses, of course, like junction, like contact, and recombination, which is also very important. In a solar cells, we try to absorb most photons from the solar spectrum. The main idea is that photons get absorbed and create an electron-hole pairs, so that these electron-hole pairs reach the depletion zone where there is an electric field which separates this electron and hole, and later they contribute to the photocurrent. If a hole and electron is separated, we can see it as a difference in charge, which is a voltage. Therefore, this phenomenon is called photovoltaics, because the light creates a voltage. But not everything in this life is perfect. There is absorption, but there is also recombination. When an electron hole is created, they have an excess of energy. Therefore, they try to deliver their energy by means of recombination. This kind of recombination is often emitting a photon. That is the inverse process of the absorption. Another way is by means of traps or recombination center in the middle of band gap, which is the most dangerous in this kind of material. This kind of recombination was studied by Courel. If we know a little from semiconductor physics, we know about the Courel explain very well the losses through the recombination, considering the defects that appear due to the poor crystallines or this kind of thing. Therefore, we'll be focused on the photon with energy lower than the band gap, as well as recombination. We must lead with these two kind of things. There are other kind of solar cells that try to solve these problems. I will lead with quantum well solar cells and superlattice solar cells, which aims at absorbing most photons that have an energy lower than the band gap, while it is important to consider recombination, because when an electron hole pair is created, they can recombine. So, taking into account these problems, the third generation comes. The third generation is mainly based on, as I explained you before, tandem solar cells, quantum wells solar cells, dye-sensitized solar cells, etc. This kind of solvers, by using nanotechnology, accounts to absorb part of the solar spectrum that in previous solar cells are lost. This is one of the main. And the main purpose is to overcome the barrier of Chalky equation limits. However, one important point to consider is that in some cases present high processing cost. Of course, that's not the case of quantum dot solar cells or dye-sensitized solar cells. In fact, there is a picture where we see the third generation, and we can produce solar cells under a low cost and under a high cost. However, it is important to consider that when we process solar cells under a low cost, there are a trade-off, because we are gaining in the part of the cost, but we are losing in the part of sometimes the quality of the material. In the case of quantum dot solar cells or dye-sensitive solar cells, sometimes it's the problem of the organics that degrade with time. This is one important topic that is on the research. But there are, we can achieve higher efficiency under the higher cost. Perhaps we can think that, oh, this is bad because we will have higher efficiency at a lower cost. But the main point to be considered is the efficiency cost ratio. In this case, for the second generation, it is important to see that in the case of silicon, the cost per watt peak is very high. That's why silicon is still quite expensive. But in the case of the second generation solar cell, the cost per watt peak has been reduced to $1 per peak. And in the third generation of solar cells, this ratio is expected to be very lower. Of course, the third generation of solar cells is a topic that is still on the study. And in this talk, I will be presenting on one of the proposals that is quantum well and superlattice. And this is a theoretical work where there is a lot of work required to improve and to get this idea into reality. We all know that from quantum confinement, we can see that density of the state can be changed from 3D to 0D. That is, when we reduce the freedom of the carriers, the density of the state is reduced. We could thought at the first that it is bad for a solar cells because we will have less absorption. But in this case, the main idea is to control the energy position so that I can control the absorption from the sun in a certain region so that efficiency increases. That's the main purpose of using nanotechnology in solar cells. So the problem is, could the well improve the solar cell efficiency? The idea is yes. The answer is yes. So let's throw a coin to the well to improve the solar cell efficiency. There is no other way to improve the solar cells. Quantum well solar cells can be constructed considering the electron affinity of the materials that are used. It is important to consider that the well is characterized by a material with a higher electron affinity. And if we have a well with a very short length or thickness, we will have described energy level. And the position of this energy level will depend on the dimension of that well. Therefore, I can control the photons that can be absorbed in that kind of solar cell. For example, this is an example where we can see the presence of two levels in the conduction band, while there is also confinement for the holes in the valence bands, and there are some energy levels, and transition can occur when a photon arrives to the solar cell from one state, electrons comes to conduction band to that level, leaving behind a hole. Schrödinger equation is the dynamic that explains what is going on in this kind of solar cells. The first proposal of quantum well solar cells was presented by Barnum in 1990. This group, which is at the Imperial College of London, is one of the main groups researching on this kind of solar cells. They have demonstrated improvement to the external quantum efficiency when quantum wells are added. In this case, we can see a shift of the quantum efficiency to lower to higher wavelength. This is explaining considering that photons with energy lower than the bandgap of the bulk material are now absorbed. In this sense, the photocurrent density of the solar cell can be increased, and as a result, the solar cell efficiency could be increased if the open circuit voltage is not highly reduced. And the main idea of quantum well solar cell is to consider a pin configuration where in the intrinsic region quantum wells and superlattice are added. That's the main idea. Okay, this is a little bit of most important equations that I use in this case. What is most important for you is that the first part is the radiative limit or the radiative contribution to recombination, while the second part is the non-radiative contribution due to the effect at both wells and barriers. Both, of course, all of these parameters are taken from the experimental part that have been reported from people working on quantum wells. This is the radiative expression and the non-radiative expression. As an important part, there could be recombination at the surface, because most of the time surfaces are not continuous because the boundaries are breaking and there are some losses at the boundaries between two materials. And the photocurrent density is calculated from the quantum efficiency of each term, the P1, the B1, the N-type, the M, and the intrinsic region, where the P-type, where the P contribution and N contribution are calculated considering the common known equation from semiconductor physics. While in the intrinsic region, it is considered the contribution of quantum wells in the absorption, and an expression of absorption is obtained starting from the Fermi-Golden rule. Of course, the impact of quantum wells is considered in this part of is also considered in this part of the fraction of the intrinsic region that are filled with the quantum wells. One of the first calculations that were performed was in the case of gallium arsenide, aluminium gallium arsenide. It is important to compare the use of quantum wells with the solar cells without quantum wells, to see the regime where these kind of solar cells are better to be used. In this case, it is considered the energy of the barrier. The energy of the barrier is the energy of the aluminium gallium arsenide, while it is also considered the width of the well. It is important to see that if we have a higher barrier and a well that is with a thickness very low, the efficiency is reduced to value lower than 1. This value of 1 means that efficiency of this kind of solar cell is equal to the efficiency of solar cell without quantum wells. If it's lower, means that efficiency using quantum well is lower. While if it is higher, means that using quantum wells, it is worth to be considered that. In this case, The condition of efficiency of normalizing efficiency higher than 1 is fulfilled for energy barrier lower. While in this range, we can see that this range of quantum well width, we can obtain efficiency that are higher than the one without quantum wells. Therefore, this kind of behavior can be explained considering that when the barrier is high, the carriers are more confined within the well. Therefore, if the carrier is confined within the well, then it is likely that the carrier recombine more easily. While if the barrier is low, there, in this case, carriers can easily escape from the well. That's the main idea, and that's the explanation why it is better to use barriers lower than barrier about, about 100 millivolts, milli-electron volts. But the main issue of using quantum wells, it is important to bear in mind that quantum wells, there is no interaction between quantum wells that are nearer. Therefore, a small portion of the intrinsic region is used. That means that we can add more amount of quantum wells, and in this sense we cannot obtain the greatest value of the short-circuit current density as wanted. On the other hand, the absorption takes place only through discrete levels. But what we want is the absorption through a miniband. Because if we have a miniband, absorption will be higher, and therefore the photocurrent density will be higher. And as an important point, increase of recombination due to carriers that are confined within the well. That is, when we use wells, we must consider that there could be an increase in the absorption of photons that are in previous solar cell configuration lost. But under the same consideration, carriers are confined within the well, which is increase their probability to recombine. As a result, there is a trade-off, and these main points lead us to propose the superlattice solar cells. In the case of superlattice solar cells, the main idea is that barriers are too thin enough to allow the overlapping of the wave function. If the wave function is overlapping, electrons are no longer localized, and they can tunnels through the superlattice instead. This, as a result, will reduce the recombination. On the other hand, it is important to see that as a result of the overlapping of this wave function, a miniband will be formed in this case of in this kind of solar cells. Therefore, absorption will be now through a miniband instead of discrete levels. There is some procedures to determine the width of this miniband. One of them, the simplest one, is by using the Kronig-Penning equation from the solid-state physics. Other approach is to consider the application of Schrödinger equation to each zone, that is the well and the barrier, and with the continuity of the wave function and its first derivative, it can be obtained a matrix relating the wave function that the wave that is that is get into the first well and the wave that is in the last well. And what is more important is the transmission coefficient. The transmission coefficient will depend with the K factor, that is a term of quantum mechanics that depend on energy, and the matrix elements M, which is defined according to the following expression, considering the contribution of each well. Therefore, from this equation, it is possible to make an analysis of the contribution of each energy to the transmission. Of course, for the case of superlattice solar cells, some points that were previously considered must be changed. One of them is the absorption coefficient. The absorption coefficient is not now through discrete levels, but through a miniband, at least one miniband. In this case, the absorption coefficient is determined once again through the Fermi-Gold rule, and it is now said that the width of the miniband is now playing a fundamental role in this kind of solar cells. Another important term to be determined is the density of the state. This is just an example that was determined in this kind of solar cells. These results were not previously published on this kind, and therefore I would like to mention that most people from experimental work have proposed superlattice solar cells, but when we observe their report, the barrier is too high so that quantum wells is quantum well isolated. Therefore, there are no superlattice solar cells, are just quantum well solar cells. Therefore, it is important to consider condition on the width. Superlattice solar cells are formed and not quantum wells. If this theory is applied for the case of aluminium, gallium arsenide, and gallium arsenide, we can see the formation of minibands with energy. It is clear observing this picture. For a well of 3 nanometers, 10 nanometers, and 20 nanometers. In a case of a well that have a which is very thin, in this case, the miniband is separated from the bottom of the material. The bottom, this case corresponds to the bottom of the conduction band when it is applied to electrons. But when the well thickness is increased, we can see that the minibands is fairly reduced, and it is also approaching the bottom of the conduction band. And this result makes sense, as if we have a semiconductor, a bulk semiconductor, what is expected is that levels approach the conduction band, turning into a traditional 3D density of the state. And the main point is we can control the miniband width considering the width of the quantum well. Another important point to be considered is the contribution of the barrier width. We see that if we have barriers that are, in this case, higher than 10 nanometers, the miniband formation is reduced. While if barriers in lower thickness are used, the miniband formation is spread. It is expected because we will have the overlapping of the wave function more easily if we have a barrier thinner. Therefore, if we want to construct solar cells considering superlattice, the barrier should be thinner enough to allow the overlapping of the wave function. But another important point to consider in this case is the presence of an electric field. Solar cells work under an electric field. The electric fields plays the role of separating the electrons and the holes. But if we have an electric field in the intrinsic region, it is important to consider the doping of each of p-side and the n-type semiconductors. In this case, when an electric field is applied, we see that we have no longer the formation of a miniband when compared with the case where there is no an electric field. This is important to consider because if we have a solar cells under an electric field, we perhaps are assuming that we have superlattice, but in this case, the contribution, the transmission of electron will be lower. Therefore, it is required to find conditions under which the tunneling conditions are obtained again. And this is why this is the effect of the electric field, and we see that the resonant condition is obtained in the first case very easily, but in the second case it is lost. In this sense, it was proposed a configuration which consists of some quantum wells, in this case it were 10 wells, where the width of the well was reduced so that the first energy is separated from the bottom. Of course, these levels were calculated by Schrödinger equation. After calculating this value and evaluated, it was obtained the result for transmission as presented in this. We can see that 60 milli-electron volts, a miniband of 60 electron volts are obtained for electrons. In this sense, I can absorb in this miniband the photons that come from the sun. While for the holes, there is an electron, for the light hole, there is the formation of miniband with this shorted, and in the case of heavy hole, it was not possible to obtain the formation of a miniband. And when these results were applied to solar cells and compared with the case of non-solar cells, it was interesting to see here that the blue curves correspond to the incorporation of aluminum to a solar cell, and efficiency, once again, is higher than the one without cells. That is, by using solar cells, by using quantum well solar cells, the efficiency can be increased with respect to the one without cells. But while using superlattice and comparing to the highest efficiency obtaining by using quantum wells, we can see that in this regime the efficiency is no higher, but in this regime about 4 clusters. A cluster, this refers to this configuration that was repeated along the intrinsic region, and we see that for clusters higher than 4, efficiency obtaining with the superlattice was higher than the best efficiency obtaining with the quantum wells. But efficiency is only 4% higher than the one with quantum wells. These results at its beginning was honestly not very interesting, because we are dealing with gallium arsenide and the barrier is aluminium gallium arsenide. We are absorbing photons that present energy higher than gallium arsenide. But what we wanted is to absorb energy lower than the band gap of gallium arsenide. At that time, this kind of there was not any material that can be used with the gallium arsenide. In fact, gallium arsenide plays a fundamental role in not only in solar cells of one junction, but also in solar cells multi-junction. Therefore, it is important to find a material that can be combined with the gallium arsenide to increase the photocurrent density. And lucky for us, this was the case of gallium indium, nitrogen arsenide, gallium arsenide. When gallium arsenide, when indium and nitrogen is used, in this case, the band gap is reduced. But at the same time, the lattice constant is kept. Therefore, we can use this material as a promising for obtaining higher solar cell efficiency. And after that, this kind of configuration was proposed from a theoretical point of view, and it is interesting to observe that quantum wells can achieve an efficiency of 21%. I am not now referring to a normalizing efficiency. This efficiency is calculating, of course, considering any kind of losses that can be presented in that solar cell. But if we bear in mind that this kind of solar cell of gallium arsenide presents an efficiency about 27%, we see that using quantum well efficiency can be increased under this condition of nitrogen concentration and well width to a value of 29%. But more interesting is by using superlattice solar cells. Of course, the same procedure was applied, and the miniband width was determined for this configuration, and the number of clusters that can be included are evaluated. In this case, the number of clusters and the cluster width, and we see that without concentration, solar cells can achieve a 32%. This is a very promising result in this kind of solar cells. And if we consider that 4-junction solar cells present an efficiency of 44% from the experimental results, by using quantum wells, these results can be further promoted to efficiency near to 15%. And this kind of solar cell is also used under concentration. The main idea of using concentration is to reduce the area of the solar cells. When concentration is used, we need less material and obtain similar values. If this material is used in superlattice solar cell on the concentration, we can see that efficiency values are approaching to 38%. Therefore, this is a proposal that currently this kind of solar cells have been used. The gallium indium, nitrogen arsenide have been proposed, and from the experimental point of view, there are some problems with the nitrogen incorporation. I believe that this kind of problem will be solved in future, and of course these results promise a high future for this kind of solar cells after solving current problems that are presented. More recently, clusterized solar cells have been attracting the attention from the scientific community working on solar cells. it is interesting to observe that once again the conduction band can be controlled, in this case regarding the selenium incorporation, and therefore once again we can construct quantum wells or superlattice. Kestrelite presents ideal property to be applied to solar cells, but efficiency is still to a 12%. There are some problems to be solved in this technology. One of the problems is the presence of some secondary phases. This is a result of our compound is obtained on the energy region of the phase diagram. But scientific community is working to obtain this kind, and some researchers have reported that they are obtaining this compound without secondary phases. Another problem is also defects in these materials, but this is still in progress. And we can see the efficiency that have been achieved for this kind of solar cells based on Kestrelite compounds, which is at 12.6%. And as mentioned, there are some problems with the defects at Kestrelite bulk material as well as the interface. These defects are dooming the solar cell efficiency to a 12%. Of course, that was the same for cadmium telluride and 6 some years ago, and now cadmium telluride and 6 are about 20%. And of course, we believe that this will be the future of Kestrelite solar cells. But the point is, okay, we have a Kestrelite that is perfect, without defect or with a low contribution of defect. What is the maximum efficiency that can be obtained using Kestrelite solar cells? It's about a 28%. This efficiency is limited by the radiative recombination. This is very low, as we can see. And once again, if we introduce quantum wells to this technology, of course, this introducing quantum well is more expensive, but the idea of more expensive go with the idea of higher efficiency. We can see that there will be a shift of the absorption coefficient to lower energy that will favor the increase of the photocurrent density. In fact, a photocurrent density of a Kestrelite can be increased from 30 to 40 milliamperes per square centimeter. That is a promising result for this technology. And if we consider the inclusion of superlattice, we can see that this technology could achieve efficiency of 36%, which is also promising. Therefore, this work aims to propose this kind of technology to improve solar cell efficiency, perhaps not now, but in a future that we think or we expect to be now very with some years now. We expect that the future is a near future. Okay? In conclusion, therefore, we have seen that we can use quantum well and superlattice for solar cell efficiency enhancement. In particular, the highest short-circuit current density are expected for superlattice as a result of the miniband formation. We see the case of gallium arsenide, aluminum gallium arsenide, which only present a 4% of solar cell efficiency increase. But in the case of gallium indium nitrogen arsenide, it was observed an efficiency of 32% that can be obtained, which is actually a very promising value. And finally, it was demonstrated that if this technology is applied to the case of kestrel solar cells, similar efficiency can be obtained, which is a promising resource for future applications. Thank you very much.
Thank you for your talk. So we have time for questions, comments.
What about quantum wires or quantum dots? I mean, in principle, if you go with the density of states argument, it should be better, is it?
Yes. In fact, the same idea can be applied to quantum wires and quantum dots. There are some people working on quantum dots in this kind of solar cells. The idea of the quantum dots is to have an arrangement of quantum dots so that a miniband can be formed. It's the same idea, can be applied without problem. Yes.
Maybe the fabrication is more difficult.
Yes, fabrication, in fact, quantum dots have been applied to solar cells, but the problem is to control the size of the quantum dots. This is one of the problems that have been presented this kind of technology. In the case of quantum wells, it is easier to control the width by the molecular pin epitaxy in this case.
And if I may, are the costs of MBE is quite expensive.
Yes.
Are the costs of the growth taken into account when you consider building this kind of?
Yes. The main, as you mentioned it, the cost is very expensive. So the idea is to obtain the highest efficiency, so this kind of technology be worst. So perhaps the application in single junction is quite limited, because efficiency, we can see that can obtain an efficiency of 36%, but without concentration. On the concentration, perhaps a 40%. But if this technology is applied to 3 or 4 junctions, to increase the short circuit current density of one of the junctions, then it could be more promising. The 4th junction at the beginning was thought to special applications, but now this kind of technology is more attractive to Earth application, considering the light concentration. In this case, I think that this kind of technology could be more attractive in a 4 junction because the efficiency will be high, and what is more important here is the ratio between cost and efficiency. Therefore, will we have a higher cost but a higher efficiency?
Thank you.
Anybody have one question?
No?
Okay, Esther, just a few questions. What are the advantages of the quaternary alloy indium gallium arsenide nitride against the ternary alloy indium gallium nitride that is usually used in this kind of devices? And the other, what is the stoichiometrically proposed 50-50? Or because when you use the ternary alloy, you can vary the stoichiometry of the indium. So that's my question.
Okay, that's one important question. Okay. The one is, sorry,
The advantage of the
advantage.
quaternary alloy.
Okay. In the case of quaternary, it is important that we take into account the fact of the lattice parameters. In the case of gallium arsenide, as we can see in this peak, if we consider another ternary, we will move from one side or another side, but lattice parameter will be different to gallium arsenide. That will introduce some defects at the interface, reducing the solar cell efficiency. In this case of the quaternary compounds, it is wonderful because we can control the lattice parameter to be the same of the gallium arsenide. And we can see here that X composition should be 2.8 of J composition. Here J refers to phosphorus. Oh, no. Refers to J refers to nitrogen composition, while X refers to indium composition. So it is not stoichiometry. There is a relation out of the stoichiometry that should come with this expression, so that lattice parameter will be the same, and to reduce any loss from the surface defects. Yes.
More questions, comments? So we want to thank again for